Good evening, Angie. How are you? Let me switch over here. All right. Hello, hello, hello. Good evening, good evening, good evening. I'm very good. I'm very good. How are you? I hope you are well. I don't know why it's so cold in my house. Has to be cold. All right. Ready for another easy day? Easy time, easy life? I hope so. Another easy time, easy life sort of day, Angie. I promise you. We just do a section and we are ready to go. What is this? Sure. Alright, it can't be found. Great. Okay. Is today an easy topic? I would say so. I would definitely say today is a super easy topic. Good evening, Pistache. How we doing? I would say today is a pretty easy topic. It's pretty chill. We've been going at one section a day for a little while. Granite, how we doing, my friend? Yo, I just got the news that Big Chibs is live? Man, is he really? I mean, I don't disagree with Big. Yeah. I'm not disagreeing with this assessment. Yeah, definitely the larger side. I don't know if I'm like big as in the other type of big. I have no idea. I'm just a dude that's certainly on the interwebs teaching mathematics. That is what I'm doing. And some other stuff. Some other things that I'm sure. Some other things that happen in and around that portion of time. Yeah. How we doing today, Granite? I'm figuring out how to cook and beat in class today. Struggle bus. Well, figuring out how to cook. That's just difficult. I didn't mean that. One of my friends used Big for a nickname in school for my girlfriend. She's 5'2" and just small in general. Fair. I'm doing good, my friend. I'm doing good. Good evening, Hisa. Good evening. Angie, I gotta be honest with you. Cooking is a forte that is not practiced in this household of one. Multitasking. Let me tell you, these hands were not made for multitasking, all right? The easiest multitasking I can do is then with one hand, I take out a pan, and then the second hand, I put on the frozen pizza, and then together, I put it in the oven and hit the bake button. And then there you go, multitasking at its finest for me. Absolutely outstanding. Like, alright. Stuffed Parmesan with the mushroom risotto. Wow, that actually does sound pretty good. Hear me out on this big brain idea. Alright, I'll hear you out. Stargazing in a picnic. Yes, would be a good idea. Agreed, granted. I agree with this idea. The only issue is that you're RNGing the weather. You have to hope that the weather's good enough for both. So if RNG is on your side, then great, you can stargaze and have a picnic. Otherwise, you're going to need a backup plan. So consider that. And you won't know the weather until, like, the day before. So if you're going to go that route, then make sure you have a backup plan just in case. All the while taking notes for class? Well, mushroom risotto and notes for class should be pretty easy. At least the notes for this section are pretty simple. UK weather's gonna screw me over. So then if UK weather's gonna screw you over, then stargazing and a picnic may not be the best idea. Because it requires outside elements to be in your favor. Bring in a large coat. Well, again, if you're gonna go stargazing, you need to be far enough away where you can stargaze, and it's not gonna be cloudy either, so. Easy, I'm not trying to burn my chicken. Oh, well, I mean, burnt chicken is healthier chicken, since you know it's not undercooked. I mean, I'm just saying, question mark. Alright. Well, you know. I got started here a little late. I'm sorry. Check that there. Oh yeah, this. That's what I wanted to do. This. I want to do something simple. Oh, I have to click 15 things to finally find it. All right. All right, ladies and gentlemen. I think we are going to be set to go. Let's go ahead and get started here with at least some material. Not a whole lot, but, you know, there's some to be had. We'll go through some of this together, and shouldn't be all that tough, in all honesty. In my estimation, it's easy. That's my estimation. Alright, let's do it. Okay, let's get started today! Welcome back to Tuesday. Hopefully you have a nice weekend. Alright, so for today, ladies and gentlemen, we are going to be moving on with Chapter 6. Okay, so Chapter 6 is what we're going to be moving on here next, and we're going to be talking more about probability here within Chapter 6. Okay, there's just a couple sections here in Chapter 6. Alright, so just 2 sections that cover the entirety of the chapter, so not too many sections, I promise you that. Alright, but today we're going over a nice, relatively easier concept, okay? I would say this is a pretty easy concept. Today we're going to be talking about random variables and probability distribution, along with its other friends, which is expected value and mean/expected value and standard deviation. We'll also talk about that in that context. All right. Now, this isn't too hard because of the fact that we actually have already talked about this in the past. You may not remember, but that's okay. That's what we're here to do. So let's go to the big board here. Let's find out what the heck we're talking about here. Let's go ahead and do it. And make sure that Angie is not burning the chicken at the same time I'm talking. All right. So let's take a good look here at the big board. Let's look at question number 1 here. So we can see we've talked about discrete continuous random variables to compute and interpret the mean and standard deviation. All right. So number 1, what is a random variable? Okay. So a random variable here is a formal definition here is a numerical measure of the outcome of a probability experiment. So its value is determined by chance. So again, the notation here for any random variable could be the capital A, capital X is pretty common. So any type of capital letter, just like we said, okay, if we take the probability of rolling a 1 on a 6-sided die, we would say, okay, let's say we have an event E. We would say a capital letter E would equal rolling a 1 on a 6-sided die. That's essentially what a random variable is going to be, and it could take on any value so long as it's an outcome in our probability experiment of some variety. Okay, so essentially 1, 2, 3, 4, 5, 6 on rolling a 6-sided die. Seems fair. All right. Now, of course, what is that going to look like here? Really quick, just so we could get a good visual representation of what a random variable looks like. So if you take a look at this table right here, notice that this table here has all these x values, 0 through 5. And we also have the probabilities associated with each of those random variables. So the probability of 0, probability of 4, you get the general idea, and then the respective probabilities that kind of go along with it. Now again, just understand that these probabilities are not necessarily need to be the same, just like this table. Right? These probabilities don't necessarily need to be the same in order for us to have a proper probability distribution. Now, let's expand on that because, of course, I'm just kind of saying words at this point. So let's expand on that just a little bit. So let's take a look here at question number 2. Question number 2 says, what is a discrete random variable? A discrete random variable is a random variable that has a finite or countable number of values. Now, we talked about discrete variables a long time ago, back in chapter 1. So back in chapter 1, we described discrete variables as like having a finite amount of values that you can plug in order to express something. So we have a variable, in this case, let's say points in a game, then that's going to be a discrete variable, for example. And a discrete random variable follows the same suit. It has a limited or finite or countable number of values you can plug in. So much like what we have here in the book. Again, you could say I have a limited number of values that I could put in for my random variable x. This would be a discrete random variable, such as in this case. All right. A continuous random variable, just the opposite here. You can have an infinite number of values. So again, instead of 0, 1, 2, 3, and 4, you could have 0, 0.11111 repeating, 0.222 repeating, and so on and so forth. 0.3114159, whatever, repeating what I did there. All right. Anyway, those two questions aren't as important as this next question here. So let's talk about this next question here. That's going to be the most important part. One of the most important parts. Number 4, what is a probability distribution? So, a probability distribution is a distribution that represents the possible values of random variables and their corresponding probabilities. So just like we saw in the table there, I'll go split screen here once again. As we can see here, again, we have the random variable, that being x, and its respective probability that goes along with it. And again, they don't have to be equal. They don't have to be the same for every single one. They could be different probabilities, but just like we talked about before when we first introduced probabilities, we do have to follow two very important properties. Just like we have here in regular probabilities, we have to follow these same two properties here for probability distributions. Number 1, the sum of all the probabilities must equal 1 or 100%. If it doesn't equal 1 or 100%, then it's not a probability distribution. So that has to happen first and foremost. Add all the numbers up together. It's going to be a probability distribution if they equal 100% or 1. And the second thing is that the probability has to be between 0 and 1, including 0 and 1. So if it has, again, if the probability is between 0 and 1, you're fine. If it's a negative value, that's not a probability distribution. If it's over 1, that's also not a probability distribution. So we can't have a negative probability. We can't have a probability above 100%. All right. That seems fair. Now, let's go ahead and take a look at these 6 tables here, numbers 9 to 14. So I want you to take a look at numbers 9 to 14 here. And I want you guys to answer a question. You guys can just post it in the chat really quick. We're just going to say yes or no to these questions here very quickly. All right, so let's take a look here at number 9. So is number 9 a probability distribution based on the definition that we have here in number 4? Is that yes or no? Is number 9 a probability distribution? Yes or no? Go ahead and type out your answer there in the chat. Yes or no, is number 9 a probability distribution? All right, Shioma says yes. All right, anybody else? No? Again, take a look at number 9 here. Remember, you want no. Well, what happens? All the probabilities are the same. But what if you add them up together? What do you get? First of all the probabilities are between 0 and 1. So that part is true. And if I add all these probabilities together here, it should equal 1 at the end of the day. So is adding up this 0.2, 0.2, 0.2, 0.2, 0.2, does that equal 1? Yes or no? So is, alright guys, I'll wait for a while. If you guys aren't going to answer, that's fine. I can wait. That is not a problem. So, either yes or no. This ain't that hard, trust me. Just kidding, yes, okay? Alright, Anna, what do you think? Yes, yes? Yes, okay. Alright, yes, alright. Again. Alright, very good. The answer is indeed yes. Okay, good. Let's look at number 10. Number 10, yes or no? Number 10, yes or no? Yes, a probability distribution, or no, not a probability distribution? Number 10. Alright. Yes. Alright. So if we add all these up together, all these probabilities here, all these probabilities will equal 1. Again, that's perfectly fine. So number 10 is yes, that's true. Let's take a look at number 11. What about number 11? Yes or no? Number 11, yes or no? Is that a probability distribution? No, yes. Okay. And take a look there at the probabilities there carefully. Hey, Athena! How are you doing, Athena? How are things? Thank you so much for the sub. I appreciate that. You're too kind to me. To say no, yes. Let's take a look here. Number 11. So number 11 is going to be no. Alright, number 11 is no. And the reason why it's no here specifically is because this last one here, you're doing some chem homework. Alright. Has it been pretty busy? I'm sure it's been pretty busy for you. So the reason why this is no here, just let me know if I can help you out in the future there, Athena. The reason why this is no here is because we have a negative probability. And again, we have to satisfy both conditions here. All probabilities must be between 0 and 1. So negative probabilities do not count. That's why number 11 is no. What about number 12? Number 12, yes or no? Number 12, yes or no? All right, guys, let's go. Number 12, yes or no? All right, yes. All right, very good. The answer is yes. So despite only one of them having 1 and the rest being 0, it still counts, no problem. Good. All right, let's move to the next one here. Number 13. Number 13, yes or no? Yes, sir? No? Let's see here. This one's a little interesting. Some people saying no. Some people saying yes. All right. Let's look at number 13 here. Number 13 is no. This is not a probability distribution. If you add up the probabilities here on the right-hand side, they follow one of the conditions. They are all between 0 and 1. But that's not the only condition that we have. And remember, if we add them up together, it should equal 1 at the end of the day. But if you add these up together, you actually get 0.95 instead of 1. And unfortunately, that just doesn't cut the mustard. Alright, so number 13 is a no for that reason. How about the last one there, number 14? Number 14, yes or no? Alright, some people saying no there. Alright, and the answer to this is no. That's correct. Okay, so the reason why the answer is no is because if you add up all these 0.25s, again, that's going to be more than 1, which means that, again, that can't happen for a probability distribution. So too bad, so sad. And that's it. Okay, very good, very good. All right, any questions so far about that? Any questions? I'll put that as a thing. There. Any questions so far? Nope. Okay. All right. So, next, let's talk about the next couple of things here. All right. So, the next couple of things we're going to talk about here is, let's take a look at number 5. All right. So, number 5 says, how do we find the mean/expected value of a discrete random variable? Okay, so here's the formula here for finding the discrete I should say the mean/expected value of a discrete random variable. Now, to kind of read this off here really quick, first and foremost, we have the notation here. Notation here is this mu of x, okay? So this mu of x is just another way to write the mean, or another way to write the notation here is the expected value. We write capital E of x representing expected value. Now, what does that exactly equal to? Now, in terms of its notation, or again in words, this is equal to the sum of all, taking the random variable and multiplying it by its respective probability. And then so basically we take that x value there, that's going to be our random variable, we multiply it by its respective probability, and then we add up all those results together after we do that multiplication, and then we get our final result about what our mean and expected value is. So we don't have to go through a super complicated process to actually find this particular mean and because we already have all the probabilities already set up and ready to go. Now, what we're going to do here next is we're going to do an example here, so that way we can see how to work with not only mean and expected value, but also how to work with different probabilities given the question at hand. Let's do an example here together, and we'll also talk about the next question here as well, which is talking about the standard deviation. Okay, so let's go ahead and do all of that here together. So let's look at the next question here. All right, so let's look at number 19 here that you see on the page. I'm just going to zoom in on this, guys. So there we go. Make sure that's okay. That's fine. All right. Okay. So let's take a good look here. We have this chart here for Ichiro's hits. So let's go ahead and read this off, and then we'll see what we can do here. So in the 2004 baseball season, Ichiro Suzuki of the Seattle Mariners set the record for most hits in a season with a total of 262 hits. In the following probability distribution, the random variable x represents the number of hits Ichiro obtained in a game. So this is the probability distribution that we have here. So x is the number of hits, 0 through 5, and then the probability that occurred during that season. Now, we're going to skip around just a little bit on purpose, okay, just to kind of highlight a few things from this table that we see here. So bear with me here for just a second. So the first thing I'm going to do here, first of all, is I'm going to go straight to letter E here. At least, let's just start off with something easy and then work our way up. So what's the probability in this case? So let's start off with something simple. What's the probability in this case that Ichiro got 2 hits? What's the probability in this case, according to this chart, that he got 2 hits? Probability that he got 2 hits. Go ahead and post your answer there in the chat. Okay. That's right. Okay, so all we have to do here, guys, that's right. Simple as that. Just look at the table. We see what the probability is for him to get 2 hits. Is exactly what's written on the table here. Is 0.2857. All right, that works. Perfect. Let's try another. What's the probability that he got 4 or 5 hits? What's the probability that Ichiro got 4 or 5 hits in a game? What's the probability that he got 4 or 5 hits? So, and if you're thinking about, don't think too hard about this. It's as easy as it sounds. And go ahead and post that answer there in the chat. .0621. That is correct. That is correct. Very good. Very good. Alright, so that's going to be the probability of 4 plus the probability of 5. Right? That's all you got to do is just take those probabilities and add them up together. They don't have anything to do with each other, so that's okay. So we take 373 and then add that to 0248. And that is correct. It is 0.0621. Okay, so by far and away, these two questions are not too hard. Very straightforward, pretty easy. Okay, no problem. All right, now let's get to the meat and potatoes of this question here. Let's go to letter C here. Compute and interpret the mean of the random variable x. So essentially what we're doing here in this question is we're just trying to find the expected value / mean of this particular probability distribution. So what exactly does that, what exactly do we do here in this case? Well, if we're going to find the mean / expected value, whichever way you want to call it here. Put this further down. Put the mean / expected value. So all we're going to do here, simply put, is we're just going to take, again, we're going to take each one of these each one of these random variables, the x values here, and we'll multiply it by its respective probability, and then we're going to add all of them up together. So here we're going to have 0 times 0.1677 plus 1 times 0.3354 plus 2 times its respective probability of 2857. All right. Plus 3 times its respective probability of 0.1491. Plus 4 times its respective probability of 0.0373. All right. Plus 5 times its respective probability of 0.0248. All right. So enter that into your calculator there. And can anybody tell me what our final answer is going to be here in this case? What is our final answer here? Anybody got an answer for me here? Yeah, no, I fully expect you to use your calculator for that. I'll just wait. Hopefully someone comes up with an answer here. I'll wait. .999? Not quite. Not quite, Jake. Not quite. Guys, stop guessing. That's not true. Plug it in a calculator, please. This will not be 1. You just have to plug this in a calculator. 0 times and 1 times and 2 times. It's pretty simple. All you gotta do is 1.6273. That is correct. Very good. So what you should do in your calculator is you should do 0 times 0.1, it's 0.1677, right? Plus 1 times 0.3354, plus 2 times 0.2857, plus, and then just follow exactly what you see there on the screen, guys. So 0.0373. All right, plus 5 times 0.0248. And that's where you get 1.6273 from. Just like so. So we should not be getting 1 unless these numbers do indeed add up to 1. That is not how it works. If we add up the probabilities, those will indeed equal 1. But that's not what's happening here for the mean/expected value. What is happening here is that you're taking each one of their random variables and multiplying it by its respective probability and adding those up together. Any questions about that before we move on? Again, sometimes with expected value, it's much easier just to write it out than it is put it in the calculator, because it could take just longer on the calculator in some cases. So, any questions so far? Okay. All right. Okay, so let's take a good look here at the next question here. All right. Yeah, okay. Actually, I should mention the last question here. All right, so let's look at the last question here is how do we find the variance and standard deviation of a discrete random variable? Now this here is a question that last time we did standard deviation. When we talked about standard deviation, we went ahead and used the calculator to find standard deviation. Now once again, we want to do the same thing here in this case. So we do have a formula that's up here on the sheet. I mean, this is nice and all, but notice that I didn't really put too much effort into this. Again, there is a reason why. As you can see here, we have the standard deviation notation here of rho x and rho x squared, which is equal to the variance. We did talk about that before. All right, but again, I still have the full expectation for you to go ahead and use your calculator here to go ahead and find the standard deviation, and you could also find here the mean/expected value at the same time. And we're going to go ahead and use this example here. And again, do I need you to memorize what you see here on the screen? Of course not. What I want you to do is, of course, apply it and be able to find it out using technology. All right, so in the last question here, and that is going to be letter D. Letter D asks, compute the standard deviation of the random variable x. So that's what we're going to do here. Letter D, compute the standard deviation here. So let's do that. So let's do D. Let's do the standard deviation here. And also, to go along with that, we'll also find the variance as well, just to showcase how we can do that out together as well. All right. So, I'm going to go ahead and shrink this down. Okay. So, first things first, everybody. Let's go ahead and take out our calculator here. Once you have your calculator in front of you, go ahead and put done in the chat. Go ahead and put done in the chat there. Type done in the chat if you have your calculator out in front of you. We can get started here together. Okay. All right. Okay. All right. Now, if you have your if you have that in front of you there, all right, let's go ahead and get started here with this one. All right, Isa's got that done. Good. Turn that down a smidge. Actually, I know how to do that. Give me a second. Turn that down. All right. Okay. So, what I want to do next here is I want to go ahead and hit the stat key here. Let's hit the stat key there. So if we hit the stat key there, and then the next thing that we're going to do here is we're going to go to edit. All right. If you have stuff in here, just go ahead and hit clear and enter on your lists. We're going to hit clear and enter on our lists here. And let's go ahead and enter in our lists. Again, we're going to have the first list L1. We're going to go ahead and enter in 0 through 5 for our first list. This will be our random variable. And list number 2 should be our list of probabilities that you see there on the right. So okay, so these are the numbers that should appear on list number 2, just like you see there off to the right. All right, right underneath my face. All right. Please type done in the chat once you have all your numbers entered in. Make sure you don't have any extra numbers put in. So once you have all your numbers entered in, type done in the chat. Okay, good, good. Looks like a few more people are working, so I'll wait. All right, he says done. Okay, good. Julian. Pistache. Anna. All right, Julian's done. Ava's done. Okay, good. All right, Pistache and Anna. So you have to so you have to go like this, Anna. You have to highlight the list. You have to highlight the list first there, Anna. Then you hit the clear key. And then you hit the enter key. And that will clear your list. So that's how you have to do that. Okay, cool. Pistache, are you okay? We got it done? Hopefully. Anna looks like she's gonna get his done. Done? Okay. Maybe Pistache had to step away. Alright, in any case, now that we got that done, alright, let's go ahead and hit the second key and the mode key. We'll go back to the main screen here. Alright, once again, we're going to go ahead and hit the stat key here. We're going to go over to calc. And we are once again going to use our good friend OneVar Stats. Now, if you have the old school calculator, what you're going to do is put in exactly what you see down here on the chat log. So OneVar Stats L1, L2. For the people who don't have the old school calculator, we're just going to go through this method here that you'll see on screen. So we'll have OneVar Stats. We'll hit enter on OneVar Stats. Again, you should have list 1 here. You probably see something like this. So list 1 should be L1, should already be entered in for you. We just have to change the frequency list here. We're going to change the frequency list to L2 if there's nothing in there. So we'll hit second and the 2 key to get L2 to show up in that spot, just like so. So second and the 2 key, and then just go down to calculate. And these are the numbers that you should see here. Okay. Please type done in the chat if you have these exact numbers that you see here on the screen. Please type done in the chat if you have these exact numbers that you see here on the screen. Alright, Big Chimpin's got that. So if you take a look at the numbers on the screen here, please type done in the chat. Let's go. Let's go. Mine says 0.1677 must be an integer. I'm a little confused what you mean by that. That's pretty strange. I've never seen that before. It should say 0. You should have 0 in your X column, Chioma, in your first list. And then you should have 0.1677 in your list number 2. So if you go back and check your lists, you should say 0 for your first, and then next to that in list 2 should be 0.1677. That's correct. Just like you see up above there, Tori. Take a look at what I entered in. OneVar Stats L1, L2. So if you're going to find L1, hit second and 1. The comma key is right above the 7 key. And then L2, which is the second and 2 key. So that's for older school calculators. It should look just like I have written up above on the chat log. Alright, cool. Chioma, did you get it? Make sure everybody's on board here. Please type done in the chat if you got this exact screen here. If you got the answers that you see here on the screen. On your calculator. For those of you who have not typed done yet, please type done in the chat. Ava, Jake. Oh, you're using a calculator app on your phone. Okay, so it probably would be a bit different. Okay. All right. Good, good, good. Anna, did you get yours? I hope Anna got hers. Yeah, I'm not sure how to manipulate the calculator app. It should be similar to what you did here, though. That's why having the graphing calculator, the 8384, is pretty important, especially for what we're going to be doing after that. So, all right. So let's take a look at what we can see here. Let's look at our results here. All right. So first and foremost here, underneath this plan that we have here, we first have a standard deviation here of 1.1785. Okay, so we can certainly put that down just like so. So 1.1785 is going to be our standard deviation for this problem. As you can see up top, we have the mean / expected value. That was the 1.6273 that we had talked about from before. Now, other things that we can also take away here. Sometimes in some questions that we asked from before, when we first talked about standard deviation, is they also ask you for variance in some of those problems. Well, we can find variance as well, and all we have to do for variance is square the standard deviation. However, in order to get the most accurate answer possible, one thing that I want to suggest that you do here is to take the entirety of the decimal here and square it, and then round at the end, okay? So, I would take 1.17847, 1345, and we would square it. So we would put this into the calculator, and then we would round after that. All right, so here our variance would be 1.3888. All right, so 1.3888 would be our standard deviation. Now notice what I did here. But the important part I want to point out to you is that, again, I didn't round in the middle of the process. I only rounded at the end of the process. So a lot of things, that's why I didn't take 1.1785 squared. That's why I actually squared the actual full length decimal here. So I do want to make a note about this. That is important, so that way you get the most accurate answers possible. And especially this is true for problems that are on my math lab, is round at the end, but not in the middle, okay? Round at the end, not in the middle, okay? Okay, so just want to point that out here so you don't get caught unawares. All right. Any questions about that? Any questions? Nope. All right. Let's go ahead and do one more problem. All right. I'm gonna do one more problem from this particular section. Okay. That's not too bad. It's just, again, takes a little getting used to. So, let's do it. Gonna move this over to the left here. Alright. So where else can this be helpful here for this like mean slash expected value? Let's take a good look here at this one. This is also a pretty classic question. So where can it be helpful for mean slash expected value? Mean slash expected value can certainly be helpful at understanding casinos or rates of return. Very important at the end of the day. So let's look at 29. Let's talk about roulette. Let's talk about why roulette is the worst game in a casino. Alright, 29. In the game of roulette, a player can place a $5 bet on the number 17 and have a 1 out of 38 probability of winning. If the metal ball lands on 17, the player wins $175. Otherwise, the casino takes the player's $5. What is the expected value of the game to the player? All right. So in this case, let's take a look at each one here. Let's talk about profit, and let's talk about its probability. Okay, let's take a look here. Let's say we win. Okay, let's say we win at roulette. Very rare, I know, but let's say we win. What's our profit if we win at a game of roulette? If we just bet on 17. What's that going to be? If we bet on 17 and we win, what's our profit in this case? How much money do we make? Okay, now I would actually, in all honesty, Anna, I probably would agree with you. I probably would agree with you here. The actual profit here, what they want in this problem, though, is actually going to be 175. But I could make an argument for 170 because it's poorly written. So, let me be honest with you, Anna. You're not wrong in actually saying 170 because you're taking 175 minus the 5 that you spent. But what they're saying for this one is you actually win 175 on top of the 5 that you already spent. So, hence why we're going to go with 175. But I can totally understand if you put 170. I'd be like, yeah, I kind of feel the same way. Yeah, no, it's not your fault. It's how it's written that actually makes it a little confusing, to be fair. That's not your fault at all. Okay. What's our probability of winning? What's our probability of winning in this case? Let's at least go with that. What's our probability of winning? One out of 38. That's right. Okay, good. Okay. Now, let's say we lose. Let's say we lose. How much, what's our profit if we lose? What money did we lose in this case? Think about it this way, right? We won 175 when we won, but let's say we lost. How much money did we lose? $5. That's right. We lost $5. That's right. So if we lost $5, if we're talking about a profit, right? If we're just comparing profits here, we're actually minus 5. We're $5 in the hole, right? So we lost. Too bad, so sad. It didn't land on the number we wanted. We have minus $5. So like, okay. So 1 out of 38. All right. Now, what's our probability of losing? What's our probability of losing here? What's our probability of losing? $37 out of 38. That's right. Okay, good. Took a little time, but that's fine. 37 out of 38. That's going to be our probability of losing. If we have 1 out of 38 chance of winning, well, then everything else is a loser. All right, fine. So let's figure out what our expected value is going to be here in this case, and we'll interpret what that means. So the expected value here, we'll take the 175. We will multiply that by its probability, which is 1 out of 38. And we're going to add to that minus 5 times 37 out of 38. Okay, and can anybody tell me, what do we get here? Let's go to 4 decimal places, I suppose. What do we get here for our final result? Pretty sure we get a negative value, so... What do we get here? Where is that? There it is. There we go. That works. Maybe? Maybe. Alright, very good. So let's talk about what this means here. Alright, and that's correct, Anna. Very good. Negative 0.2632 is the correct answer. Alright. Very nice, Jake. That's correct. Now, let's talk about what this means. This means that for every time we play roulette, on average, we're losing a little bit above 26 cents per play. So 26 cents per play. So this is like making it, let's make an assumption here that we have an infinite amount of cash and we can play an infinite amount of times. What's the average loss that we make every single game? Well, we lose 26 cents to the dollar every single game, okay, on average. All right, so, which is pretty bad, guys. That's pretty awful, okay? In fact, that's really, really bad, all right? So, if we're losing about 26 cents every single game, let's look at the second half of the question. If you played the game 1,000 times, how much would you expect to lose? So already in the question, they expected to lose money. So if all you have to do here is you play the game 1,000 times, how much do you expect to lose? Well, 26.32 cents, that's about 26 cents. So we'll say about 26 cents if we're going to go by just dollars and cents. So we go minus 26 cents here times 1,000. Okay, if we played it 1,000 times, then we're expected to lose $260 over the life of playing 1,000 games. So these are really bad odds. Like, this is why you should never play roulette, because this is essentially what happens. You will definitely always lose more money than you win at the end of the day. That's typically what happens pretty much down the gamut. So, yes, that's how we can also see what, how much, the only 2 games that you probably should ever play at the casino are probably blackjack and poker. It's probably the only 2. Poker with other people because you're not playing against the house. And then blackjack because they have the best odds of possibly winning against the house with strategy. So, it is possible, so. Alright. Any questions about that? No. All right. Very good. So that, in a nutshell, everybody, is going to be section 6.1. Okay. That's it. That's all we gotta do for today. Simple enough. All right. All right. Any more? Hopefully, no more questions. Any more questions for today? Or are you guys good? I think that's all we really need to do for this section. Next time, we're going to be doing much more with the calculator. So please be sure to bring the calculator with you next time, because we're going to be doing a lot of different things with. We're going to be doing some different things with the calculator. Next section can be a little bit tougher, so be sure to be prepared for that. Okay, great job everybody here today. Nicely done. All right. Very nice work. If you're going to keep up with the material here, we're up to section 6.1. All right, that's where we're at. All right, great job today, everybody. Thank you so very much for coming on out here to the stream once again. All of you are absolutely fantastic people. Thank you so much. I appreciate all the time and the effort you guys come to make. You guys come here, you make a good effort. We try and do things. I know sometimes I'm a little harsh, but trying to have you participate and stuff like that, that's kind of important. All right, yeah, I can do that. Sure. Show you question 4. There you go. You can go ahead and take a screenshot of that. That's fine. Okay. All right, everybody. We're gonna come back here, same time, same place, on Thursday. All right, and we're gonna go ahead and get started with section 6.2. There's only 2 sections here in chapter 6, so it's not very long. We're just again just plotting through here, but again, I'm gonna be a little bit extra careful for next time. Okay, definitely gonna 6.2 is gonna keep us on our toes for just a little bit. All right, have yourself a wonderful evening, everybody. Have yourself an absolutely wonderful evening. All right. Please take care of yourself, everybody. And I'm going to switch back to the big cam here. And do this. All right. Take care, everybody. And we will see you all next time. And as always, everybody, stay safe, stay healthy, but most importantly, stay sane. All right. Take care, everyone. We will see y'all later. All right. All right. Have a great one. Take care, everybody. Bye. Bye, everybody.